In this lecture, we will discuss about the Eulerian graphs and as an application of the directed graphs, we will see where these graphs are being used in decision theory making. We had seen what is a directed graph. The difference between the directed graph and the undirected graph is that the edges are being oriented. Almost all the definitions that are true or that are defined on the undirected graphs also holds for the directed graphs. We had seen what is meant by a directed walk. So, using this definition of directed walk, we will define what is meant by an Eulerian line, and from that we will define an Eulerian digraph. The second part would be characterization of Eulerian digraph. When you look upon the graph, you can decipher whether the graph is Eulerian digraph or not. And the third part will be the decision making using the directed graphs. So these three parts will constitute this particular lecture. Now I will formally define what is meant by an Eulerian digraph. You have a directed walk, from vertex ui to uj. What is meant by directed walk? You have a sequence of vertices and edges. Alternatively, you have to start from ui and end at uj, and the orientation of the edges should be from the preceding vertex to the vertex following it. So this will be called as a directed walk. Suppose if I write u1, u2, u3, so in this case you have a directed walk from u1 to u3. The edges are oriented from u1 to u2, and the second edge is oriented from u2 to u3. So this is the directed walk. The directed walk is said to be closed. It is said to be a closed walk if the origin and terminus are same, or if it starts from the same vertex and ends at the same vertex. So that is called as the closed walk, directed walk. And if you take a closed directed walk, when it traverses or when it moves along all the edges of the graph G, then such a closed walk is called as a directed Euler line. Similarly to the undirected graph, that is called as an Eulerian trail, where the edges are not repeated. Similarly here, you have to go through all the edges. You have to go through all the edges of the graph G, and that you have to travel only once, not more than once. So when you travel to all the edges exactly once, then in that case, that is called as a directed Euler trail. And the definition of the Eulerian digraph comes here. If you have a digraph which contains a directed Euler line, then such graphs are called as Euler digraph. A digraph containing a directed Euler line is called an Euler digraph. So basically, it begins like this. Start with a directed walk, make it a closed directed walk, and you also see to that all the edges of the graph G are travelled exactly once, and then if it is possible, then such a graph is called as an Eulerian digraph or Euler digraph. I have taken an example here. You can see that when I travel through the edges A, B, C, D, E, F. You can see that I start and end at the same vertex, travel through all the edges exactly once. You can see that I have I travel through all the edges exactly once. So this graph is said to be an Eulerian digraph. And now, when I just look upon this graph, can I identify whether this graph is an Eulerian digraph or not an Eulerian digraph? And if you look at every vertex in the graph that I have given here, you can see that the sum of in degree and the sum of out degree are same. So, when I take any vertex and if the sum of the in degree vertex or in degree and the out degree are same for every vertex, then such a graph is said to be an Eulerian digraph. You would have seen what is meant by a balanced vertex or balanced graph. A vertex is said to be balanced if in degree is equal to out degree. And the graph is said to be balanced if in degree is equal to out degree for every vertex u in graph G. So, when you take a balanced digraph, then that graph will necessarily be an Eulerian digraph. So, this is the characterization which I have already given you as an hint here. What is the statement? A digraph G is an Eulerian digraph if and only if. When I say that if and only if, both the conditions are true. G is connected and balanced. That is, when a graph G is connected and balanced, then it will be an Eulerian digraph. The other way is also true. When I take an Euler digraph, it will necessarily be connected and balanced. Balanced implies the in degree and out degree should be same for all the vertex. And when you want to prove such theorems here, if and only if condition, you have to prove the necessary and sufficiency part. So assume one, prove the other. So that is the concept here. First I will assume I will assume that G is an Euler digraph. And now my aim is to prove that it is connected as well as every vertex is balanced. And when I say that G is an Euler digraph, then the graph G has a directed Euler line. Okay, directed Euler line. Before moving into the next part, let me give you the connectedness here. The digraph G has a directed Euler line. And now you can see that because it is a directed Eulerian line, it is obvious that it is connected, because you know that in an Euler line it has to pass through all the edges exactly once. So naturally it has to be connected. It has to be strongly connected. In fact, it has to be same. So the first part is true. That is, the graph G is connected. Now I have to show that the graph G is balanced. So I proceed ahead. You have a directed Euler line. Now go back to the definition of the Euler line. What is a directed Euler line? It is a closed directed walk that traverses through every edge of the graph G exactly once. And when it travels through exactly once, every edge exactly once, okay, and if I take a vertex u in the graph G, I will have one vertex, one edge directed towards the vertex u, and the another edge leaves the vertex u. So naturally, because I have to come into that vertex through one edge and I have to leave that vertex through another edge, I cannot have the same edge. And another thing, if it is the starting point, I start from one edge and end through another edge. So for every vertex, I will have one edge directed towards that vertex and another edge leaving that particular vertex. And when I have such a combination, then the incoming degree and the outgoing degree or in degree and out degree of a vertex will be same. So in this case you have d plus u is equal to d minus u, and this is true for every vertex u in V. So you say that the graph G is balanced. So now obviously you can see that this is very simple. Let me again repeat it. G is Eulerian digraph. If it is an Eulerian digraph, it should have a directed Euler line. And when it has a directed Euler line, it has to travel through all the edges exactly once, and therefore the graph G will necessarily be connected. I have to prove the balancedness of the graph. For that, what I do is I take that G as a directed Euler line. Directed Euler line is a directed walk which is closed, which travels through all the edges exactly once. And when I fix a vertex, I will have one edge coming towards that vertex U and another edge leaving the vertex U. If it is the starting vertex, I will have an edge which leaves the vertex, and I will have another edge which comes into that vertex at the end. So naturally, every vertex will have in degree and out degree to be equal, and therefore I say that the graph G is balanced. So the first part is true. The second part is obviously easy because the graph G is balanced. That is the assumption that we make. So d plus of u is equal to d minus of u for every u in V. And what is the definition of this? There is for every incoming edge, there will be a corresponding outgoing edge, because d plus u is equal to d minus u in degree. Suppose if I take in degree of u as 3, I will have 3 edges coming into the vertex u and 3 edges leaving that particular vertex. So how many times I enter into the vertex, I have a distinct edge which I have not already traveled, so that I can select an Eulerian line, and if I have an Eulerian line, then I say that the graph G is an Eulerian digraph. So when you look upon the graph, if the sum of the if the in degree and out degree of every vertex are equal, then you can conclude that the given graph will be an Eulerian digraph. Now we will move to the third part, as I told you, how to use the directed graph in decision making. Now I will give or explain it through an example here, and depending upon the situation, you can construct or model the problem using the directed graphs and use the technique and arrive at the conclusions. So the example that I am going to take is, I am going to rank a number of objects by comparing 2 at a time. Okay, I will be comparing 2 at a time, and this is called as the method of paired comparisons. And this comparison is done using these directed graphs when the numerical measurement is not possible or very difficult. And you can also compare not more than 2 at a time and then arrive at a conclusion. So as an example for this, if you have a product, say 10 products, you have to rank those 10 products. Okay, one would have superior quality, one would have less price. So you have to make a comparison of all the parameters and decide upon the ranking system. So in such cases, we can use the directed graphs for making a scientific decision. As an example to the decision making problem, I take a simple one which you can extrapolate it for the other situations. In a college, an election is to be conducted and three candidates participate in the election for the post of the president here. We call them as A, B and C. Every student is asked to cast their vote by making one of the choices which is given here. So I have just given the enumeration of the positions of the participant A, B and C. So when I want to cast my vote, I have to choose between C1 to C6. What is this C1 to C6? C1 is the choice A, B, C. What is this A, B, C? My first choice is A, second choice is B and the third choice is C. Suppose if I choose C3, my first choice would be B, second choice would be C and my third choice for the post of president would be A. Suppose if I choose C5, it would be CBA. First choice for the post of president is C, second choice would be B and my third choice would be A. After the election is complete and after the counting is being done, it is seen that for C1 you had 100 votes and for C2 you had 500 and for C3 we had 425. C4 we had 75, C5 and C6 are 350 and 50 respectively. So now we have to decide the winner. Usually what we do is, I have A as the first choice in C1 and C2, B as the first choice in C3 and C4, and C as the first choice in C5 and C6. C1 and C2 put together gives you 600. C3 and C4 put together gives you 500, that is 425 plus 75. And C5 and C6 put together gives you 400. So when I count the number of votes based on the first choice, I get 600 for A, 500 for B and 400 for C. Naturally, I decide that A is the winner. But there are certain votes, namely in C3, where the choice of A is in position 3. That is 425. Candidates have opted A as the last option for that particular post. But when you look at C5, 350 as voter what requires C to be the president of the club. So you have a difficulty in matching the winner or finding the winner. Of course, one part is just adding the number of votes depending upon the first position or first choice. You will have A as the winner. And if you see that C has got the lesser votes, but when I use the technique of the directed graphs, we could conclude that C has got more influence than A and B, which we will see in the subsequent part. And I have already told you, when I count the number of votes for the first choice, I get A to be 600, A gets 600, B gets 500 and C gets 400, and therefore I can conclude that A is the winner. Now I use the digraph technique. I create a node or vertex for every person. And now I am going to compare person A and B, number of votes obtained by A as well as B. The number of votes that A is in a superior position than B, that is A is in first choice, B is in second choice, or A is in second choice, B is in third choice. And these choices, A has got a superior position than B, in three choices, C1, C2 and C6. You can see that C1 A is 1, B is 2. In C2 A is 1, B is in 3. And in C6 A is in 2 and B is in 3. So the number of votes wherein A is in a superior position to B is at C1, C2 and C6. I just add the number of votes C1, C2 and C6. I get 650. Similarly, now I find the number of votes that B is in superior position than A. That is obtained in the remaining part, C3, C4 and C5. And when I count the number of votes for choice C3, C4 and C5, I get 850. And you can see that A is in a superior position than B has got 650 votes. And B is in a superior choice than A has got 850 votes. And you can see that 850 is greater than 650 and therefore the voters prefer B over A. 850 is greater than 650. 850 is greater than 650, yeah, and therefore I conclude that B is preferred over A. So now I am not going to discuss how do you construct the edges. So for every person you create a node. Now I have to construct the edges and see that the edges are being constructed in a peculiar way which suits the convenience of everyone. So for that, what I do is I see the superior position of a particular person with another person. Say I compare now A and B, position of A and B, and I conclude that B is the preferred person than A. Now I move to the comparison between A and C. Now I compare two at a time and therefore this is called as a paired comparison. Now I will also explain how do you get this tournament. Obviously it will be a tournament because I will be comparing every pair of persons. And you know that in a tournament you will have a directed edge with at most one direction. Okay, one direction. So that is called as the paired comparison and tournament which we will be using here. So now by using the same technique I compare A and C. A is in a superior position when compared to C in three choices, C1, C2 and C4, and the number of votes for C1, C2 and C4 is 675. And now C is a superior position than A in 825 cases, namely for choices C3, C5 and C6, which has obtained 825 votes. And you know that 825 is greater than 675 and therefore C is preferred over A. And now if you look at this, obviously C is preferred over A. Okay, C is preferred over A, and in the previous case we had seen that B is preferred over A. So now I have to make a comparison between C and B because now A is out of the race because B is superior to A, C is also superior to A in the number of votes that they have obtained depending upon the positions in the choices. So now the election is between B and C. So now the crucial part comes here. I make a comparison in the positions of B and C. So now first one what I do is I take B is in a superior position than C, and that occurs for choices C1, C3, C4, and the number of votes that are obtained is 600, 100 plus 425 plus 75, 600. And the second one would be CB. What is CB? C is the superior position when compared to B, and that is obtained for C2, C5 and C6, which would be 500, 350 and 50, and it comes to 900. You can see that 900 is greater than 600, and therefore you say that C is preferred over B. C is preferred over B. So when I compare B and A, B is preferred. When I compare C and A, C is preferred. And when I compare C and B, C is preferred. So obviously C would be the winner. But now, how do you construct the digraph? So now B is preferred over A. Therefore, I draw an edge from B to A directed towards A. And now when I take A and C, C is preferred over A. So from C, I have an edge towards A. And when I compare B and C, C is preferred over B, and therefore I have an edge from C to B. And now if you look at this, the vertex A has got two incoming edges. Vertex B has got one incoming edge and one outgoing edge, and C has got two outgoing edges. And you can see that the graph that we have constructed is a tournament because you have one directed edge. Okay, the direction can be in any way, but here I have a direction wherein the vertex C, at the vertex C, you have the edges emanating from C or more number of edges emanating from C, and therefore I conclude that C would be the winner. But when you count the number of votes for the first position, you could see that C was last. Okay, but C had a greater influence in the among the students. By construction of the digraph, we were able to decipher the influence that C has over A and B, or over the students when compared with A and B. And based on this, you can also declare C as a winner. And these are the techniques that are used in the games when you have a tie. When you have a tie among the teams that play each other. So these are the techniques where these digraphs can be applied in decision making. And as I told you, this is only a simpler example. You can model the digraph in some other situation, and you could also try how to get a scientific decision making or using the digraphs. Okay. With this, we come to this end of this lecture. If you have any queries, you can mail me at venkatakrish2@max.sastra.edu, and I will be answering your queries.